All right, we are going to do some solving of trig equations in this example over here, but I'm going to do a side-by-side comparison so we could see visually why my answers are affected or impacted, because as the inside of this parenthesis here gets fancier, as we multiply numbers in front of theta, we are going to have more and more interesting things happen. So I will probably throw after this another example in where I'm going to use a little multiplication in there as well. So let's get started. Here, both of them start with the same first two steps. If we're solving for theta between 0 and 2 pi, we want to get theta alone. In both examples, I'm going to start by adding 1 and then dividing by 2. I probably don't need to write out that work for you guys, so I'm just going to go ahead and write sine of theta minus 3 pi over 4, which is all in parentheses for me right there, equals, and remember I added 1. If you need to show the work, please just show the work for yourself. And then I divided by 2. So I have 1/2. And here the same thing. I have sine of theta, only theta, with or without parentheses, that doesn't matter, equals 1/2. This one's a little bit easier, lighter version of the example. So if you wanted to ask yourself the appropriate question in order to solve it, sorry, fix that lighting for you. You would say to yourself the sine or y value in the ordered pair of what angle on the unit circle between 0 and 2 pi equals positive 1/2, angle or angles. You could do that in your head, or if it's not on the unit circle, you would have to take the sine inverse of both sides. You do not divide by sine. You do not divide by cosecant or cosine or any of that. You do not change it into something. You, to get rid of sine, take a sine inverse of both sides. We don't really need to write this step because these are answers we know from the unit circle, okay? That would leave, this would be gone. Theta equals the sine of what angle or angles equals 1/2. So it's still asking that same question that you could just ask yourself up there. But like I said, if it's not on the unit circle, you would need a calculator, and this is how you would use the calculator. However, if this was a 1/3, which we should probably talk about again soon, you would get only an answer in quadrant 1. We did in lesson 11 or 12, we talked about trig inverse as a function and how it only gives you answers in one quadrant when it's positive, one quadrant when it's negative. But we know between 0 and 2 pi, I have this answer sine being 1/2 in 2 places. So even if you use a calculator, you still have to do work yourself on top of that to finish a problem. Keep that in the back of your head. Anyhow, what angle or angles should I write down for this question? I've done this example about 100 times with you. Anybody want to say?
Pi over 6 and 5 pi over 6.
Thank you. Pi over 6 and 5 pi over 6. Okay, now how does this relate to this? Well, if I show the work the way I said it, which isn't really necessary here, it might be helpful. If I take sine inverse of both sides, sine inverse of the sine of theta minus 3 pi over 4, close, equals what you do to one, you do to the other. Sine inverse of 1/2. Then these are gone. And instead of being left with just theta, we're really left with theta minus 3 pi over 4 equals, and this we just did over here. We know it's two different answers. It's pi over 6 and 5 pi over 6. Since we're solving for theta, in order to get theta alone, what do I have to do next? It's just another layer to the problem. That's all. So what do I have to do next in order to solve this problem? I need to isolate theta. No one in the chat or
Pi over 4.
yeah, all you're doing is, thank you, is adding 3 pi over 4 to the other side. So I'm going to add it over. Now, since I have two options for this, I would set up two little equations for myself just so I could show it a little bit better. So I'll draw some lines here. So one equation I can write is theta equals pi over 6 plus, I forgot if it was plus or minus, 3 pi over 4. And the other equation will be theta equals pi over 6, nope, 5 pi over 6, sorry, plus 3 pi over 4. Now on this set of examples, the example right before this one, we did things like this. And always, everything sort of foreshadows what's to come. When it seems a little out of place, it's on purpose. So when you watch something on Netflix and you're binge watching and the preview before the episode tells you about a character from like 10 episodes ago, and you're like, why are they in the preview? That was such a long time ago. They're probably going to be in this episode, you know? So same idea. I reviewed adding, subtracting, common denominators, all that stuff, because it's in this episode, okay? So my common denominator would be 12. And I can do, if you multiplied both sides of your equation by 12, you would straight up get rid of your denominators and then you would divide it at the end. It's up to you how you want to do this to add things. If you just want to find the common denominator the classic way, well, you would multiply this guy on top and bottom by 2. You would multiply this one on top and bottom by 3. Now they both have a denominator of 12 technically. So in this case, theta equals 2 pi over 12 plus 9 pi over 12, which equals, so 2 pi plus 9 pi over 12, which is 11 pi over 12. So my answer that was originally pi over 6 is now 11 pi over 12. Which answer is bigger as an angle, pi over 6 or 11 pi over 12?
11 pi over 12.
Yeah, that's definitely bigger because that's 2 pi over 12, right? It is bigger, and it's bigger because of this step here, and we'll elaborate in a minute. As for the method where you clear out your fractions, if you are anti-fraction, I'm going to take this, so I'm doing both of these a different way. You could do them whatever way you like, as long as you get the right answer. If I multiply everything by my common denominator, my least common denominator of 12, my next step, I would get 12 theta. I'm just going to go like this so it doesn't look like that. 12 theta, because I multiply both sides, equals, I mentioned when we first did this that when you multiply, PEMDAS was a lie in a way, and you can divide before you multiply. 12 over 6, 2, times 5, 10 pi. 12 over 4 divide is 3, then multiply times 3 pi plus 9 pi. That gives me on the right, I'm not cut off, right? 10 pi plus 9 pi is 19 pi. Here I have 12 theta, and then you could just save that divide by 12 for the last step. So if you prefer that, because to you it's cleaner, and sometimes these get like a little intense, then do it that way. So here I have 19 pi over 12 and 11 pi over 12 as my answers for this example. Whereas for this one, I had the answers of pi over 6 and 5 pi over 6. So I would say that we solved, even though it's trigonometry, I would say we solved these problems algebraically. How was that for you guys? Thumbs up, thumbs down, we're good, a nod, kind of okay, like you're getting it, right? Now attach it back to the pictures of these things, okay? So if I looked at that one that said, the one that I had on the right side, actually, I guess I'll keep them in the same order. So this one said 2 sine theta minus 1 is 0. This is us solving a system of equations. I could have gone up a level, gone back a step, and I could have seen y equals 2 sine theta minus 1 and y equals 0. And directions saying solve the following system of equations. And when you solve that system, we spoke about this a couple weeks ago, we could solve by substitution, elimination, or graphing. And if I take what y is equal to, here it's 0, and fill it in there, I can solve by substitution. And that would essentially be this step. That means every equation has a picture that goes with it. The graph of 2 sine theta minus 1, you may or may not have learned graphing trig last year. And even if you did learn it, you may have forgotten it. I did review just the parent function of sine theta. I'll kind of talk through it again slowly, just a sketch. I'm not going crazy. But does anybody remember the graph of y equals 0? What does that look like?
A horizontal line along the x-axis.
You're the best, thank you. The horizontal line at y equals 0, which is the x-axis. The slope is 0 because we don't have that mx plus b happening. So it's rise 0, run anything. So except 0. So we just have a horizontal line. Slope is 0 at y equals 0. That is actually the x-axis. Now we also have that. Okay, the parent function, sine of theta, if I had just that little baby example, y equals sine theta, will be right here. I showed you guys the best way to graph that is to just do one cycle, and I'm going to do my max of 1 and my min of -1. Why? Well, that's the biggest and smallest sine can be. Sine is opposite over hypotenuse. The biggest it can be is 1. The smallest it can be is -1. Then I'm going to put tick marks of 0, pi over 2, pi, 3 pi over 2, and 2 pi. So you have 5 fingers. You're going to have 5 tick marks. My first tick mark is actually going to be at the origin, so you kind of don't see it. Between your 5 fingers, you have 4 spaces. Each of those 4 spaces is a quadrant. First tick mark to second tick mark, this is quadrant 1. I don't know if I'm flipped for you guys, so sorry. Second to third tick marks, this is the second quadrant, third quadrant, 4 quadrant, okay? 4 quadrants. So I'm going to mark those up. There I will have, I'm just sketching this a little on the side, 0, pi over 2, pi, 3 pi over 2, and 2 pi. I'm about to ask you, what is the sine or y value in the ordered pair on the unit circle? You should have that memorized. What is the sine at each of these angles? And hopefully we can jump in and participate, answer that. So what is the sine? This axis is my theta. This axis is my y, or y equals sine theta, my output. What is the sine of 0? You could just shout it out.
0.
Good.
0.
What is the sine of pi over 2? You're picturing the circle.
1.
Good. 1. At pi over 2, that top angle, the y value is 1. You went up 1. What is the sine at pi?
Is it 0?
It is 0. It's the far left. The y value is 0. You're on that x-axis again, you know? Now, you have to also remember, like, these are like parallel universes. This graph is the regular xy plane graphing an equation. This lives in the universe of y equals x squared being a parabola on your graph. This doesn't live in the universe of the unit circle. That's like a weirdo universe where we use the xy plane to help us have a cheap trick method to figuring out sine and cosine. Parallel universe, it's not the graph of sine and cosine. It is just a tool we use to help us figure out the sine and cosine. All right, what's the sine of 3 pi over 2?
-1.
Thank you, -1. It's a little low, but I just don't want to squash it. And what is the sine of 2 pi?
0.
Yep. So that is one full cycle. You should be finishing at 2 pi where you started at 0, since they are what kind of angles? 0 and 2 pi are what kind of angles? Starts with co, ends with terminal.
Is it equilateral angles? Because, you know, that starts with co and ends with terminal.
Thank God you're joking, Chris, because I was just I just
Yeah.
got so, like, my depression level just like completely
the facial
plummeted.
expressions that were very, coterminal.
Thank you. Oh my God. Well, you have to know, like, it wouldn't be that unusual to have someone do that to me. So whatever.
Yeah.
Now, if I stick arrows at the end, I don't draw the arrows. If you guys remember polynomials, they would draw the arrow going way up and way down. And that was basically their way of saying, like, hey, this is going to go up forever and down forever. Trig isn't like that. Since sine on the circle repeats, periodic, cyclic, same thing over and over, I don't draw those arrows going all the way up and down like that. Sometimes they just kind of leave them as this little nub over here. And sometimes we even kind of curve it a little just to kind of show, like, hey, this is going to do this forever. Thank you. All right. So there we go. 2 over here better. 2 in front of the sine theta and a -1. Be a brave soul. If I graph this, knowing that this is the parent function of sine, what do I have to do to my parent function if I want to graph 2 sine theta -1?
Would you move it? I'm just taking a guess. Would you move it to the left?
Well, left and right movement is the one that we look in the parenthesis or crazy house. That's what
Okay, so then
mentally
you
prepare
have
for
to
this
left-
over here though, okay? Look where I'm pointing. I didn't finish
Okay.
writing it, but if I flip back over here, that in your brains, okay? So start marinating, guys, because it's going to come up. So you want to fix your answer now?
I'm not sure. I'm just like
Go for it. You're spitballing.
Yeah, I don't really know. I would just say like either reflect. I don't know.
Well, reflect is with a negative sign being multiplied in front. I'm going to do a little quick thing. I'm not going to ask for participation. I'm just going to go ahead and do this. Like, I'm going to do the square root of x because I feel like it's actually helpful because there's no symmetry. Square root of x looks like this. Yeah, well, pause, hold that. Let me just finish this thought. If I put a negative in front of square root of x, that's this type of reflection. It shouldn't be stretched out. It's not my best drawing, sorry. If I do y equals square root, sorry, negative x, now it's inside with the x. What that does is it reflects it that way. Obviously, I should have planned a little better so I could put them all in a row here, but if it had both, in this case, again, I like this example because it doesn't flip back to become itself like x cubed or the cube root would. This would be here because it reflects both vertically and horizontally. If I have y equals 2 square root of x, I'm going to, just so you can see the difference, okay? If the original is this, this would be like this. It's going to go like that. Okay. That's what you were just saying, Makai, I believe. Y equals, if I don't know which way I want to do this now. Let's do, I guess I'll do this. 2 square root of x inside. I'm gonna have to be very careful drawing this, so I'm just gonna switch. Okay. If you have this 2 on the inside, this would be the original. Put a dot there. The 2 it would be this. Now, I'm going to add in, I don't know what color, my red pen. Looking here, they are directly next to each other. It squished it or compressed it closer to the y-axis. Here, it pulled it up further away from the x-axis. Out here, vertical stretch. In here, crazy house, this is a horizontal compression. It squeezed it that way, okay? It's getting sunny again. I'm gonna have to move the curtain. Sorry, I'll fix it in a second. And then just 2 more. I'm not gonna go full blown, but just for compare contrast purposes, y equals square root of x minus 3 versus y equals square root of x minus 3. This would be here. This would be there. So a little squished. I'll fix that light. Okay, so that's just a little compare contrast situation. Hopefully that's going to help us grasp it when we apply it to trig, because it's literally the same thing every time you graph anything. Okay? So, got it. So you can take a picture, write it down, mental picture, whatever you do. I'll just go this way. So go ahead, Makai, did you want to continue then? Was that you, or who was telling me what we have to do for this?
Yeah, it was me, but I don't really like. I get what you're saying, but I just need to listen.
Okay, what if I did this right there? Now my dog is trying to jump on the window ledge with the curtain closed. This is not going to work. If I put those parentheses around it, there's nothing in them. So this is more like the one that had the -3 next to the square root. And it's a -1. What does the -1 do? And what does the 2 do? Going once. Going twice. Sold to no one. So the 2, did somebody want to do it? I don't know if I heard it unmute. The 2 is going to be a vertical stretch of my graph. It's going to take my regular sine wave that goes up to 1 and down to -1, and it's going to stretch it vertically by 2. So this will be, so I'll put a red star over here. It'll be twice as stretched out first. That's what that 2 does. Vertical stretch of 2. And then the -1, anybody want to try it now? You feel any braver? We'll move. Shift your graph which way?
Downwards.
Yes, down 1 unit. So then this whole thing moves as a whole package down 1. So I'm going to go over here. I'm going to go to -1. I'm going to draw that right over there. Okay. And I'm going to use that as like my new midline. Sometimes they call it a midline. I like the fancier name for this because I think it sounds fancy and smart. So this is called a sinusoidal axis. And I actually heard, I don't know, you probably don't know who Sandy Munro is, but he's like this engineer genius guy that like takes cars apart and puts them back together and just dissects everything and analyzes everything and what could be better about it and whatnot. And talking about all the engineering and the mechanics of it. He actually used the word sinusoidal for something. I don't know how it applies to cars and engineering, but hey, fun word right there. And then I'm going to basically draw the same picture here, but stretched up to 2 and -2 from my new middle. Not that hard. Ready? 0, 5 tick marks. 1, 2, 3, 4 more. I hit my quadrantals. Pi over 2. Pi, 3 pi over 2, 2 pi. Okay. Then on here, I'm at 0. 0 doubled. I didn't change. It's still 0. At my next tick mark, I'm stretched up 2 units. So I just go up 2 from here. 1, 2. So I'm up here at 1. So coincidentally, I still hit +1 at the same place. Then here at pi, I'm at 0 again. Here at 3 pi over 2. Down 1, 2 units. So I'm actually down at -3, okay? Because that's -2. And then back here at 2 pi, I'm back at 0. So my graph, it shouldn't be that sharp, it should be round, sorry. Here, and then concavity switches a bit over here, and show a little arrow. There's my new graph, okay? That's all it is. It is literally one parent function, and you apply the transformations to it. So it's probably simpler than you thought. Question, Makai?
Yeah, so if it was like a half, would it just be the same thing, but just flip? Okay, I see what you're saying.
It's going to be
So
squished. So it's going to be like a little baby wave, like a little scallop,
Okay.
little guy.
Okay.
All right.
Got it. Thank you.
Yeah, no, good that you asked. So there we go. And now the other one, y equals 0. I'm going to grab we'll do the orange highlighter for this. So y equals 0. We were told, I think Zareen told us it's the horizontal line at the x-axis. So there's that one. And then y equals 2 sine theta -1. This I'm going to draw in pink, and we're still solving where do they intersect between 0 and 2 pi. That's what you're really doing this whole time. Now, graphically, it's not really that hard, not that really that easy to tell where they intersect. But do my answers make sense? Think about when I picked up my hand and I talked about the quadrants. This is quadrant 1, quadrant 2, 3, and 4. I have an answer in quadrant 1. I have an answer in quadrant 2. Does that make sense? Look at this on the previous page when we solved it algebraically. Here's my answers. I have an answer in quadrant 1. I have an answer in quadrant 2. That's solving algebraically and using the unit circle. Here, solving more of a graphing approach, I have an answer between 0 and 2 pi. Yes, that would be a quadrant 1 answer on the unit circle. I have an answer here between pi over 2 and pi. I don't mean quadrant 1 on my graph of sine in this paper right now. Clearly, they're on the positive x-axis between quadrant 1 and quadrant 4. That's not what I'm talking about. This region between 0 and pi over 2 indicates quadrant 1. This region between pi over 2 and pi, that's quadrant 2. Quadrant 3 is between there, and quadrant 4 is between there. So we have 2 answers still. So stretching and shifting up and down, not too dicey. When do things get dicey? When we shift left and right, because when I shift left, these 2 points, if I shift left too much, do you see that they won't be between 0 and 2 pi anymore? Like it will literally push them out the window. So you would do that. You're still going to start with those 2 answers. You're going to get negative answers, but they won't work. Then what you'll do is you're going to add to find the next answer of each one. The way we found those general solutions, we used n as an element in the set of integers. We're going to add to it and find what the next ones would be, because even though you push these 2 out of view, the next 2 will get pushed into view. So this shifts. It's the same pattern over and over and over, like when people do pattern tiles or whatever. So if I go like this, you're like, I'll take care of you. I'm going to push that out of the way. Okay, cool. But now these 2 popped in from the next curve. And you're like, oh no, I have 2 more over here. So it's like whack-a-mole. You push it over, that's gone, but 2 more popped in, okay? So that example, graphically, was 2 sine theta minus 3 pi over 4, was it? I already forget. Yes, yeah? Minus 1. Is that right? Yeah. So thinking about that now as it relates to the graph, let me see if I can make this. There we go. As it relates to the graph as well, here was the parent. Well, the parent, and also we stretched it out. Here is the more basic example as a system. I could do this as a system, y equals 2 sine of theta minus 3 pi over 4 minus 1. I still have, sorry, I still have a vertical stretch of 2. That red stretch that I did on here, I also still have it shifted vertically or down 1 unit. That's the same, but I have an extra transformation inside of my parentheses. I was foreshadowing that change over here. What happened to my graph because of the minus 3 pi over 4?
It's going to shift to the right.
Yes. So everything's going to shift to the right. Crazy house. Everything moves to the right. So really, I would take this, and actually, I'm not even going to do it. I'm going to go here. Everything on my graph is going to go to the right. I'm going to start it this way. It's going to go to the right 3 pi over 4 units. Now, how big would 3 pi over 4 be? Well, 3 pi over 4 is like the middle of this. This is obviously not drawn to scale, so it's about that big. So I would take everything and move it over that much. So instead of this point being here, I'm going to go to the right 3 pi over 4. It's there now. Instead of this being here, I'm going to go to the right 1, 2, 3 pi over 4. It's here now. This to the right 1, 2, 3 pi over 4. To the right 1, 2, 3 pi over 4. To the right 1, 2, 3 pi over 4. And then I'm going to go ahead and draw my new graph. This is, I think you could see the blue through the blue. This over here then will be, again, not my best artwork. I'm just connecting dots here. Here, here, there, and there. But that was only one cycle. And we're only looking between 0 and 2 pi as per the directions on the previous page. 2 pi is here. And 0 is here. I'm only looking between 0 and 2 pi for answers. My two answers are about here and here, where the blue and orange intersect. Oh, that orange is not even showing up now, right? So probably, is that better if I do that? And there you go. All right, so it's two answers here. But if you were to graph this, you wouldn't make yourself crazy and kind of graph it like by shifting the original. We'll get to that when we graph trig later on. But here's our big bonus example to make a big brain. Big bonus example for big brain. Ready? Y equals, I'm going to keep it all at 1/2 stuff, okay? I guess I could look at it as a system again. 2 sine 1/2 theta minus 1 and y equals 0. Or solve, same idea. Either way, I'm looking between 0 and 2 pi only. Or solve 2 sine theta. What am I doing? 1/2 theta minus 1 equals 0. So if that's the case, either way, if you were doing this, that would be your first step, more or less anyway. What should I do next? So sine 1/2 theta minus 1 is 0. I would start it like the others, right? Add 1, divide by 2. Sine of 1/2 theta equals 1/2. Next step, again, same as the others. I'm going to take sine inverse. Sine inverse of the sine of 1/2 theta equals the sine inverse of 1/2. Sine and sine inverse, adios. I'm only left with 1/2 theta equals, I had two answers for that. I'm still going to start with those two answers, pi over 6 and 5 pi over 6. What should I do next?
Multiply by 2.
Yep. Theta equals, multiply by 2. Don't write 2 pi over 6. We could reduce, divide before you multiply. Pi over 3 and 5 pi over, why am I writing 6? 3, because I multiplied everything by 2. And when I did that, I reduced it with the 6. Originally, pi over 6 is in quadrant 1. 5 pi over 6 is in quadrant 2. What quadrant are each of these answers in? Pi over 3 is in quadrant what?
1.
Yeah. And what about 5 pi over 3? Quadrant
2.
4.
4. Quadrant 2 ends at pi, which would be 3 pi over 3. So it's definitely bigger than quadrant 2. Graphically, visually, what did the 1/2 do to the graph? Think about where they started. They started in quadrants 1 and 2, but then my two answers transformed, and now they're in 1 and 4. What did this 1/2 inside do to the graph? The graph that I just had.
A horizontal stretch of 2.
Exactly. It took my pink graph here and pulled it and stretched it horizontally by a factor of 2. So everything doubles how far away it is from the y-axis. So that's why the two answers that were here and here stretched out. And instead of me fitting the whole graph between 0 and 2 pi, how far out would I need to go to fit one full cycle? If I stretched it, go ahead.
0 and 4.
4 pi.
4 pi, yeah.
Yes, exactly. It's going to take us twice as long to cover that full cycle if I stretch it by a factor of 2. So that being said, as a quick sketch, I'm not like being all that serious with it, but instead of it being pi over 2, it's pi. Instead of 1 pi, it's 2 pi. Instead of 3 pi over 2, it's seriously just 3 pi and then 4 pi. That's still 0. Down 1 unit. Stretches of 2. -1 is my, does anybody remember the name of the axis? The dotted line?
Sinusoidal.
Thank you. Sinusoidal. Good. Then something like that over there. Now it looks like, oh, sorry, that dot should be here, not up there. This graph might be like, well, it looks exactly like the last picture. It is. What's different is how I labeled it. If I only want answers between 0 and 2 pi, that wanting to know where does it equal y equals 0, which was the horizontal line at the y-axis. That's that right over there, okay? That's what I'm looking for. Then I have an answer here when I just crossed the orange, and I have an answer there where I crossed it. Down here, got nothing. If I go in and put my other split in half, that's pi over 2, and that's 3 pi over 2. These are where we see the quadrants. This is quadrant 1, 2, 3, and 4. So the answers I can find, that's a quadrant 1 answer. If it were drawn to scale, I'm sketching, kind of close, and quadrant 4. So when we start doing this, these are called solving equations with multiple, even if it's not any more or less than usual, solving equations with multiple angles. That's what we call it. If you ever look it up in a textbook, if you're ever searching for more examples like this, that's what this would be called. So you're not just solving trig equations when you are playing inside this crazy house situation. Now the stretch, what if I didn't want to know when it equaled 1/2? If I asked when does it equal -1/2 between yellow and yellow, between 0 and 2 pi, when does this graph equal -1/2? Or rather, it was -1/2 over here. Okay, it was -1/2 over here, not. So if I made this a +1 instead, I suppose. Yeah. Or either way. But do you see how this never ever dips down to the negative area here when it's stretched out that wide? It equals 0, or what could I make it instead? Like anything, -2 or -3. If I wanted to know when this graph equals anything below here, if it never happens, you would say no solution, because it might push all your answers out the window. But bad example, I'll pick another one later. So you might have fewer when you stretch it. That's why it's important to know if it's a stretch or compression. And then I also talked last time, if we compress instead and squeeze it, that's where you increase your frequency of the waves. So your sound waves are like up and down a lot in a little amount of time. You might have more answers. And that's where we're going to get into solving that. And you have to remember that n is an element instead of integers thing I showed you guys. To best find all of the answers, because you could have several and there's like a systematic way to do it. You don't have to do some weird guess and check or anything like that. All right. So I know this was a heavy thing, but I just kind of wanted to cover everything since I'm recording. And I have anytime that you guys, we have a few minutes left. So are there any questions that you want on the recording before we move on? So go ahead, Jason, you have a question?
Yeah, so is the reason that you decided to go by pies for the intervals instead of the just the basic unit circle intervals because 5 pi over 3 is close to 2 pi? Is that why you decided to do that?
No, there is a whole system to it, that how I pick. So I'll kind of let you in on my brain over here. when I graph sine, am I flipped? Yeah. When I graphed sine, I used my quadrantal angles to graph it, right? And it was easier than like, usually when you first learned to graph things when you were younger, you probably learned by making a table and you would plug in numbers and connect a lot of dots. I don't need to connect a lot of dots right now. Like if I plugged in pi over 6, it would be like over here, I'd get a half. If I plugged in pi over 4, I'd get 0.7 root 2 over 2. If I plugged in pi over 3, I'd get like 0.86, it's over there. If I plug in 2 pi over 3, I'd get 0.86 again. 3 pi over 4, 0.7 again. 5 pi over 6, I'd get 1/2 again. I don't want to do this all day. So I pick these points because at the quadrantal angles is where all the good stuff happens, you know? That's where it's all interesting. So I pick those because that's going to be my middle, which is 0, my biggest, which is 1, middle, or my lowest, -1, right? Like the lowest thing I could get. And if I just know those points, I can draw my graph. Now, if I take this sine graph and I know those 5 points, those are my 5 finger points, are the best points to use. But I put a 1/2 with theta. Then my 5 finger points that I had were 0, pi over 2, pi, 3 pi over 2, and 2 pi. By putting the 1/2, we said it was a horizontal stretch by 2. So I'm going to literally double all of these. 0 doubled is 0. Pi over 2, pi. Pi would become 2 pi. 3 pi over 2, which is 1.5 pi, will become 3 pi. And 2 pi will become 4 pi. So it doubles it. Now there's another way to do this. You know how we said, and again, this is for the graphing lesson, so you're getting a big head start, but I don't mind, so it's all good. You could call this letter or number, the constant we use sometimes is B, and sometimes I use a capital B for it. So I might write that my trig equations are of the form A sine parenthesis, or actually I would normally keep the B on the outside, but we'll talk about that again in the future. B parentheses theta. Sometimes I use C and D because I'm going A, B, C, D, but I'm going to use theta minus H. And I'm going to use plus K because that should be a little bit familiar to you guys a bit. So A and B. A is what we used anyway when we did vertical stretches and compressions, probably lowercase a. And now B, I used lowercase b with my classes last year when we did horizontal stretches and compressions. When I ask what the period is of a graph, the period is how long it takes for a cycle to repeat itself. So how long is the period for sine of theta? How long does it take for it to start repeating itself in general, normally? Chris, you want to say?
Yeah, it's within 2 pi.
Yes. So you could say 2 pi. From 0 to 2 pi. So how long is that? 2 pi. Now, so the period is normally 2 pi, but there's a formula. So P equals 2 pi. Normally that's a 1. And the period is what's affected by a horizontal stretch or compression. So the formula that we use for a period is 2 pi over B. If you divide it by B, it'll flip it and do what you want it to do. So when that was a 1/2, what's 2 pi divided by 1/2 the same as?
Two pi times 2,
Which is?
4 pi.
So instead of my graph going from 0 to 2 pi, it goes from 0 to 4 pi. Next thing, again, this is all, I'm just sprinkling this into your brain since we got 3 minutes, whatever. These here, to figure out like how far apart the first point is from the second point, what I do always is I take the period and I divide it into a certain size. What number should I divide the period by to find out how big each of these spaces are? Think of my hand example, but think carefully. What number should I divide the period by to figure out how big each of these spaces is? Did someone say?
5? Would it be?
Not 5,
4.
by 4 quadrants, how big it is. Okay, so if I do, and I also remember like in the alphabet, LMNOP, Q. So period is the whole thing. Next letter in the alphabet is Q. It's a quarter of it. So what's a quarter of the period? Well, when it was 2 pi, a quarter of it was pi over 2. I would divide 2 pi by 4. That's pi over 2. Now I have 4 pi. So what's 1/4 of 4 pi? Well, a quarter of it would be pi. Why is this useful? Well, you don't always start at 0. Like here, I start at 3 pi over 4. So that's this blue graph. If I wanted to figure out where to put the next points, I need to figure out the period, divide it by 4, find a quarter of it, and just add that amount on 4 times. So you'll already have 1 point from your shift, and then you add the quarter period 1, 2, 3, 4 times, and you'll have 5 points. Bloop, draw your graph, and you're done. I love graphing. Beautiful. So this was all me sprinkling it in. So Jason, I hope that answered your question why I used 1 pi, 2 pi, 3 pi, 4 pi, whatever, instead of those over there. It'll make more sense when we get to the actual graphing unit, but I really think it's important that you guys have a visual representation of equations when you're solving them, because that will help you know, like, oh, I got 6 answers for this. Why did I get 6 answers? I usually would only get 2, but it's like, oh, you had a compression by factor, you know, of 1/3, or you tripled your frequency. So yeah, if you normally only had 2 answers, well, now your graph is 1, 2, 3 cycles squeezed between 0 and 2 pi. So it makes sense to get 6. So if you could just like kind of have that connection in your brain somewhere, I don't need you to be a pro at graphing yet. When we get there, you will be a pro. I'll make you a pro. But until then, I just like, this is good to know that you're doing the right thing when you're solving. Your answers make sense, that you should have fewer or more or less answers than what you normally would get. Okay. Any other questions while we wrap this up? No? No one? Okay. Well, and also as for graphing, we're not going to graph things like quadratic trig, like sine squared and whatnot for right now. So don't worry about that. And then with the number 6 on the handwritten examples, another trig, solving trig problem. Did it have powers in it? What was that one like? Like I said, I only have 1 through 4 here. I'm just going to end the video now. If you understand if you end up rewatching it and you understand what I'll just say to you guys for the videos, you could give it a thumbs up if you get it, but if you don't, give it a thumbs down. Like, I want to know which ones you guys are confused on. So things that get lots of thumbs downs, I'll be like, they need help with this. So I don't care if it's got like a lot of negative feedback, that's fine. So go ahead and do that, but hopefully this helps clear things up if you watch it again later.